So yesterday we looked at evaluating functions. And remember, evaluating means that you're essentially plugging in some type of x and you're getting the value, the y value of the equation. Today, we're going to be doing operations. Operations with functions is a little different sort of goal because an operation is like adding, subtracting, maybe multiplying and dividing. And so now we're not really plugging in, but rather we're operating. We're trying to combine by using addition, subtraction, multiplication, division. Let's see how this sort of plays out. Now, one of the things about today's lesson is that there's some notation. And mathematics has notation. It just means that we need to understand the notation so that then we can actually simplify the problem. So this notation, f plus g of x, it actually just means f of x plus g of x. Why didn't we write it that way? Well, we could, but I'd like you to realize that whether it's written the first way or the second way, it just means that we're adding two equations or two functions together. So I got my f function, I got my g function. All I got to do is put a plus sign between them. And when you put a plus sign between 3x plus 4 and 2x minus 3, you have a pretty easy problem. You're just going to combine like terms. And of course, those like terms give you 5x and plus 1. The parentheses weren't really necessary. They didn't really change anything in the problem because, again, it was just addition. But when you get to subtraction, that is f of x minus g of x, then the parentheses matter, especially the parentheses of the second function, because I'm now subtracting everything in that second parenthesis. Sometimes students like to think that you're distributing the subtraction sign. That's totally fine if you want to think of it that way. Now you can just combine your like terms, and that's why we're actually just going to get x, but now plus 7. So when you have a subtraction sign, you do want to be very careful, especially with those parentheses. Moving on, we have f times g of x, which really just means f of x times g of x. For this particular problem, that means taking your 3x plus 4 and multiplying it by that 2x minus 3. Now again, I'm putting the parentheses around because, well, they do matter. When you're multiplying two binomials, we typically call that like the FOIL method or the distributive property. And so I want to multiply the first together. I get a 6x squared. The next group together gives me negative 9x. Continuing, I get 8x. And finally, negative 12. And when I add those like terms together, that is the x's, they will become just negative x. Of course, I still have my 6x squared and my minus 12. And finally, we have a division problem. And division problems are the same thing as fractions. So I can even write this as f of x divided by g of x. I'd like to add a little something new to this for you guys, because when you have a fraction, you have a denominator. And there's something about denominators, they can never equal 0. And so when we write answers that are fractions, we also give the little disclaimer that the denominator can't equal 0. We'll say that g of x cannot equal 0. What does that mean for our specific problem? Well, once again, take your f, your 3x plus 4, make a fraction now, so put your 2x minus 3, your g, put that in the bottom, and then, oh, yeah, you're not allowed to have the bottom equal 0. Now, what do I mean you're not allowed to have the bottom equal 0? Well, that means that like 2x minus 3 can't equal 0. But that means that 2x can't equal 3. But that means that x can't equal 3 over 2. And so we put a little disclaimer. We say that x can't equal 3 over 2. Yes, you want to actually solve the problem that is the denominator. You want to solve that denominator so you can get the specific x value that you can't equal. What is this? What is f plus g of 1? Well, it's combining a little bit of yesterday with today. You see, f plus g of 1 still means I'm going to add my functions together. But it also means that we're going to plug in 1. So wait a minute, if I'm going to add my functions together, that's still my 3x plus 4, and then my 2x minus 3, but I'm supposed to plug in 1. And when I plug in 1, well, really, that means that it's not going to be the letter x, but it's going to be the number 1. I like to just plug it in at the same time. Most of you will want to do that also. And so now I can actually calculate the value of each of these. I can do the parentheses. Of course, 2 times 1 minus 3 is going to be negative 1. And then eventually 7 plus negative 1 comes out to be 6. So it's a little combination problem. We actually added the equations, but we also plugged in 1. What's that you notice? You could plug in 1 to the answer that you got up here. Sure, if you plug in 1 to the answer, that also will come out to be 6. So it kind of depends on when you want to do the plug-in. Like I said, most people will plug it in like I did here. They'll just plug it in right away. But you could also plug it in to your answer. It'll still come out the same. Now, the problems that we did in that chart, let's be honest, none of them were supposed to be too terribly hard. The problems that we're going to do in this chart or these boxes, yeah, they're a little bit harder. They're a little bit harder simply because they have to do with fractions. And anytime you have fractions, things just get a little bit harder. So let's do f plus g, but let's do it with these fractions. Now, f plus g just means I'm going to take the first fraction, x over x plus 1. I'm going to add the second fraction, x minus 1 over x plus 2. Fun times, adding fractions. Yes, you need a common denominator. Now, the common denominator means that both fractions have to have the same denominators. And right now they don't. But they will if I multiply by what is missing. If I multiply by what is missing from each denominator. So notice that x plus 2 was missing the x plus 1. So I multiplied it. But notice that the x plus 1 is missing the x plus 2. So I multiply by it. Now I actually multiply the top and the bottom. Do you notice? That's how you do a common denominator. You have to multiply the top and the bottom. Okay, things are going to get a little more interesting here. But first of all, I see that my denominators are the same. I see that my denominators are the same. That's good. That means they're common. But I see that my numerators are changing. In other words, I need to simplify them. And so I do a little distributive property. You get x squared plus 2x. I do a little bit more distributive property. Maybe the FOIL method, if you like to call it that. I get my x squared, and then I get some x's to cancel, and then I get a minus 1. Now, we're almost there. What we need to realize is that I did all of this so I can actually add my numerators. You add the numerators because the denominators are common. Well, the only thing that really happens is that the x squareds add to be 2x squared. I still get the regular 2x and I still have the minus 1. How about this denominator? Yeah, they're both the same, right? So it's not going to change. It's going to be the same denominator. Unless you want to also sort of FOIL or distribute that, which is fine. Sometimes you will see the answer with the denominator also simplified. A comma, right? Yeah, a comma. Whenever you have an answer that's a fraction, you have to give a little disclaimer. The little disclaimer is to talk about what x cannot equal. Now, what do you mean what x cannot equal? Well, remember, the denominator cannot equal 0. That means -2 would be a bad number. -1 would be a bad number. Why? Because it makes the denominator equal 0. So we can say x could not equal -2 and -1. Let's do some more fraction fun. F times g. Now you already know that that means you're just going to multiply. So let's go ahead and jump right in. We're going to multiply the first fraction times the second fraction. Good news. You don't need a common denominator to multiply. You don't need a common denominator. Instead, you just multiply. You multiply across, not cross. You don't cross multiply. Don't do something like this. You just multiply across. And when I multiply across, I'm going to end up getting, well, I'm going to end up getting like a distributive property, x squared minus x. And when I multiply across, I'm going to be getting more like a FOIL method. Yeah, that's right. It's the same thing that we got up above. Okay, but I multiply. So that's it, except for the comma and the little disclaimer. And because it's the same denominator, it's going to be the same disclaimer. And finally, I have a division problem. A division problem. Now, this is going to look a little weird, and then we're going to fix it. It's going to look a little weird because if I take f and I try to divide it by g, I end up with sort of like a complex looking fraction. I end up with basically a fraction within a fraction. Actually, I have two fractions within a fraction. Doesn't look a lot like a lot of fun, does it? So instead, let me suggest something better. Let me suggest that we think about dividing as a good old division sign. So f divided by g, divided by x minus 1 over x plus 2. Why is that better? Because it's supposed to help you see that anytime you're dividing, that's the same as multiplying by the reciprocal. The reciprocal what? Yeah, the reciprocal. That's just going to be like the flip of my fraction. So I take this division sign and I change it into a multiplication sign by doing the reciprocal or by multiplying by the reciprocal. And now I've just created another multiplication problem. How do you do multiplication problems? That's right, you just multiply across. You just multiply across. So I end up with x squared and 2x because I do a little distributive property here. And I end up with x squared minus x plus x. They cancel, and then just minus 1. What's a bad number? What's a bad number? How about -1 and 1, right? So x cannot equal plus or minus 1. Fractions. Okay, yep, they're a little harder. They have denominators. And depending on if you're adding, multiplying, or dividing, we have to carefully work with each of those denominators. So what do you think? Can we kind of put this all together? I believe that these examples were meant for me to give a little instruction and then you to maybe try a little bit on your own. So f plus g of 2. Now listen, there's numerous ways to think about this. It is an addition problem. You do have a number to plug in. Maybe it'd be a little bit helpful if we just kind of rewrite this using the notation from the front if we just rewrite this as f of 2 plus g of 2. Does that make you feel a little bit better about what to do with the number 2? I'm just going to plug in the number 2, and I get the number 3. I get the number 3. And I'm going to plug in the number 2, and I get, oh, well, I actually get the number 3 again, just kind of coincidence. And so this ends up being 3 plus 3, which is 6. You want to try it for the second one? Are you maybe rewriting the problem? You can rewrite it as g of 1 divided by f of 1. Plug in 1, and you get 0. Plug in 1, and you get 1.5. Turns out, though, that 0 over 1.5 is just going to be 0 anyway. It is defined. You are allowed to have 0 divided by something. It's just going to come out to be 0. And then how about down here? It's honestly just kind of the same thing, but we have a graph. Most students prefer to kind of rewrite this using the notation on the front. Remember that this -1 and this -1 are both x values. So I go to x equals -1. Now when I go to x equals -1, on the f graph, I find the y value to be, again, x equals -1, but I find the y value to be 2. On the g graph, when I go to x equals -1, I go up and find the y value to be 1. 2 minus 1 ultimately just comes out to be 1. You want to try that last example? I find it helpful to rewrite it. F of 2, over here on the f graph, f of 2, that's when x equals 2. You get a y value right here. You get a y value of 0. And on the g graph, when I go to 2, that is x equals 2. I go up to get the y value, which happens to also be 2, but it's just 0 times 2, which is going to come out to be 0 anyway. Function operations, adding, subtracting, multiplying, dividing, and a little bit of mixing up with what we did yesterday. Now it's your turn. Try these homework problems. I've tried to mix up as much as possible, give you some variations as you continue to work through these concepts with functions.